so before getting, oops, I have to get used to writing with this pen. So before getting into the core of the lecture, let me first introduce the objects that we will try to study. So it won't be Lie groups, it will be finitely generated groups. So what does it mean to be finitely generated? So usually I will write F, G groups, maybe like this. Okay, so I hope you can read it. So you start with a group G, and you assume that there exists a finite set S in G, such that each time you pick an element of your group G, you can find elements S1, Sk in S that enables you to write G like that. So every element is a product. Any element of your group G is a product of elements of your set S. And so what is important here is that S is finite, of course. And so we will try to understand those groups by looking at the way that they act and the way and as a geometric objects. So before that, let me first give an example that will be fundamental. It's three groups. If you've never seen them, let me start. So I will give you the first example is the free group on two generators. But of course, you can have any number of generators. It's just to simplify the exposition. So this is the free group on two generators. Okay, so you start with an alphabet. So in our case, I will call them A and B because I have only two generators. And then I define abstractly A minus 1. So these are formal inverses of my generators. Okay. And from there, I can define a set of words. These are finite elements tuples that you can write from letters A, B, and their inverse. Okay, and where I set A to the power 0 means that it's the empty word. So for instance, A, B, A minus 1, A, B, B, A squared. This is an element of, it is a word of 1, 2, 3, 4, 5, 6, 7, 8 letters. Okay? And so what is the law that we put on this group is a concatenation of words. So for instance, I have that one, and then I pick another word like AB. I can make the product. So what I obtain is A, B, A minus 1, A, B, B minus 1, A squared, and then I add AB. So if I want, here I can write instead A to the cube. Okay, and so this gives you a law on the set of words. And what you can see is that the empty word is a neutral element, because if you add nothing, then nothing happens. But what is missing is an inverse, because here it's really a monoid. So what we do is that we say that each time we see B inverse, we can simplify. And the same with A inverse. So let me, how should I find? I don't know where I have the eraser. Ah, here it is. Okay, so here, oops, sorry. Here it was B. What's going on? Ah, okay. B inverse. So now, what I wanted to say is that when I see one letter in its formal inverse, I replace it by the empty word. And it's the same for here. Okay, so then what I obtain like that with this equivalence relation is that this will be the same as A cube B. Okay? So do you have any questions up to now, or is it okay? So with this, I obtain a group structure.
Hello, Peter.
And a word where you have more. Yes.
Peter.
Yes, Arena.
Can you make it full screen? Full screen?
It's not full screen?
No, it is half. It's coming half.
Oh, wait. Like that?
Yeah. That's okay. Okay.
It's good. It's better like this?
Yes. Now we can see.
Ah, I'm sorry.
No. Okay.
Okay, so this is a very simple group in some sense, because what you do is just you concatenate words, and when you see one letter in its inverse, you simplify. And when there's no simplification, a word is reduced if there are no simplifications. And so each time you pick a word or you concatenate two words, you can always simplify, and there is a unique reduced representative, which consists in getting rid of all the letters and their inverses, and then you proceed inductively. For instance, if you have something like A, B inverse, A inverse. So first, you can simplify B inverse, and you get A inverse, and this is the empty word. So in some sense, the inverse of AB, it is B inverse, A inverse. Okay, because what you do is you switch the letters when you go to, when you pass to inverses, change the orders. Is it okay? So what is important with this? So I will change screen if I can. I don't know how to do it, of course. Here. Is that each time if G is a finitely generated group with a finite generating set S, then I can consider, instead of taking only two letters, I take all the letters in S. And then it defines also a free group, and then I have a natural morphism in G. This is a group of morphism. And so what does it consist? You pick a word in the letters of S, S1, Sk, and then you associate the element inside G that is represented by this product. So you make S1 times S2 times S3, and then up to Sk. Okay? And it's very easy to check that this is the group morphism. And so the universal property of groups will tell you that your group G will be isomorphic to the free group on the letters coming from S divided by the kernel of this map. That means that every finitely generated group is always a quotient of a free group. And in this sense, it makes the free groups very interesting, and we usually look at what's going on with free groups when we try to test some property or something like that. Okay, so now what I would like to do is how to see a group as a geometric object. Okay, so, group as geometric. So do you have any questions up to now, or can I continue? So the first thing is to define the word metric. Okay, so for this, we start with a group G and a generating set S. And so you're going to look at, you're going to define that the norm of an element G with respect to the generating set S, it will be the minimal cardinal that enables you to write the word in terms of the generators. So each time you pick an element G, there's no reason why there should be a unique way to write it as a product of elements of the generator. So you look at the most efficient one. And this is the norm that you, some sort of norm that you obtain. And then you define the distance between two elements. Let's say X and Y. So of elements X and Y. So for X and Y in my group, okay, so this is just, I have to do it the right way. I think it's X inverse times Y. Okay? And so you can check that this defines the distance. So now, distance on the group G. Sorry. Okay, and so what is interesting with this distance is that the group will act by isometries on the left as taking the same definition as what Arendam did it, meaning that if G is an element of the group, I can look at the distance from G times X and G times Y. And what is this? So by definition, it's the inverse of Gx times Gy. And so this is the same as the norm of, so what is the inverse of G times X? It's X minus 1, G minus 1, and then I multiply by G and by Y. And so what you see is that G inverse and G, they cancel, and I'm left with X inverse times Y. And this is exactly the distance in S of X and Y. Okay. So what I did like that, with this word distance, I create I see the group like a metric space, and it acts on itself by multiplication on the left by isometries. Isometric action of G on my metric space G, distance with respect, word distance with respect to this. Okay? So this remains rather abstract at this point. So what we are going to make things a little more concrete, I will now define what is a KE graph. You just see the board.
We can see you.
Any questions? Not yet? Okay. So then, if you're okay, I'm going to switch screens and define the KE graph, if I can. Okay. So, KE graph. You change colors. Okay, so what is it? So the data is always the same, a group G and a generating set. Okay, and now I want to define a graph. X. So this graph will depend on the group and also on the generating set. Okay, so how is it defined? So the vertices V is exactly the elements of the group, and the edges, so it will be the set E, it will be everything you can write down of the form GS, where S belongs to S or is in inverse of your element. Okay? And so let me give an example, several examples. Let me start with G is equal to the cyclic group Z. So we know that Z is generated by 1 and minus 1, because any integer is a sum of ones or minus ones if it's like that. So in this case, the set of vertices are all integers, like this. So here you have 0, 1, 2, 3, 4, minus 1, minus 2, etc. So now I put an edge between one integer and one integer plus or minus 1. So from 0, I can go to 1. Oops, sorry, I can go to 1, but I can go also to minus 1. And I can go to minus 2 or to minus 3, etc. Each time I add minus 1. On the other hand, I can go on the right. And so what you see is my graph here is just like the real line with integers that are marked. And what you can check, so it's an exercise that is what you'll see, I guess, tomorrow, is that if you look at the embedding of the group with respect to the word metric inside the KE graph, then this is an isometric embedding, meaning that it preserves the distances. So here what I say is that each edge, I give length 1. Okay? So this is, it is distance preserving. Okay? And what is interesting also, because I multiplied on the right, is that I also have an action on the Kelly graph. G on X. So for the set of vertices, if I have a point X, a vertex, sorry. And I see G like an element of my group, then the extension of G of X is just left multiplication. So this is a new vertex. And now if I have an edge, I look at G times X, X times X, then this is just the edge G of X, Gx times X. Okay, so what you see is that left multiplication yields an action by isometries on the Kelly graph. So now what is nicer than just looking at the word metric is that we obtain something that is connected. So properties. The action, so the Kelly graph G is connected. Balls are compact. So the fact that they are compact, we have only finitely many edges that leaves any vertex. So we have also finitely many vertices into your graph. And then you also have an action G on X by isometries that is transitive on the set of vertices. Okay, and the quotient. So in this case, the quotient, what you obtain is just one vertex for all the group. And then here, because it's plus and minus one, you have just one loop like that. Okay? So it's a compact, the action is also co-compact, meaning that the quotient is the compact graph. So now I could have chosen another set of generators. For instance, I could take T to be 2 and 3. So this is indeed a set of generators because 3 minus 2 is 1 and 1 generates the whole group. So now, how does the new graph look like if I take T as a set of generators instead of S? Well, now I can, to what is attached 0? Well, it will be attached to 2 because I can make plus 2, to 3, to minus 2, and to minus 3. And now 2 is attached to 0, but also to minus 1, and also to 4, to 5, and 1 it will be attached to minus 1 as well, because it's minus 2 from 1, and also to minus 2. And you see, you obtain something that is, the graph is different, but it looks a little bit the same if you go from far. And so what I would like to do before the end of this lecture is try to see how can we understand the structure of the Kelly graph to which and can we get rid of this dependence one way or another? How can we look at all the Kelly graphs of a given group without being too specific? And so this is something that is important because if each time you pick a generating set, you have something different, then you might prove something that only depends on the generating set, and this is not what we want to do in geometrical theory. What we want is to be able to apply geometric methods to understand the algebraic structures of the whole group, not of the group with a generating set. Do you have questions at this stage? Okay, so if not, I will give you a look at another example with a free group, for instance, if I can switch. Sorry, I don't, here. So let's say another example is the, oops, black free group. So I will start with my group on two generators. So now how do we proceed? I start with an empty word, my neutral element. And so I see my group generated by A and B. So first I can multiply by A. So this is in red, I'm sorry. So this is A, and it leads me to my element A. But I could also do A minus 1, or I could do B, or B minus 1. Okay, so I'm cheating a little bit because I have to change colors this time, and it's a little difficult. Okay, and what you see is if I want another word, if I multiply by A, then I will get A squared. Okay, but, oops. And if I multiply by B, then I will get AB. Okay. Oops. It's not that convenient. Okay, and if I multiply by B inverse, then I will get AB inverse. Sorry, it doesn't work. What's going on? I cannot change colors now. Okay. So here I get AB. Now if I multiply by A back, so I'm coming back to the, okay, it's working again. I'm coming back to the neutral element. So this one I don't add. And then I continue. So then I will get A to the cube. Oops, I should continue in red. A to the cube, A to the fourth, etc. And what you see is that I'm building a tree where each word can be given like that. So the Kelly graph, what I want to say here is that the Kelly graph is a regular tree of valence 4. Because at each vertex, I have exactly 4 elements, 4 edges that stick out. And when I look at the quotient, what I will obtain is, as usual, one sole vertex, a single vertex, because the action is transitive. And then I will have 2 edges, one for A and one for B. Okay? So here I forgot that one. Okay, so you see that depending on the group, you can have something that is very different. And so what we want to understand is how can we use the geometry of the Kelly graph to say something about the group? And this is a whole program, and you will see many examples of that during the school. And so let me check my notes. Yes. So for this, I want to introduce to go a little at a different level and speak about geometric actions. And I would like to prove for you the fundamental lemma of geometric group theory. So here, what is interesting, maybe before I switch, is that you see, if you look at a path inside your group, the path of shortest length, it will give you the word distance and the way to write it down. So for the free group, in the free group, oops, sorry. So seen as generated by A and B, that is the natural set of generators. The word length is equal to the number of letters. Oops, sorry. I'm writing here number of letters of the reduced representative. Oops, but this is French. Okay, so this is very specific to the to groups like that. Usually, you can have there can be several elements of the group in the set of generators with a minimal cardinality. So, but not for the free group. And that's why you have this is a tree, because you have for each word you have a unique reduced representative, and so you have no loops there. So you see already this combinatorial property of the free group can be read from the Kelly graph, saying that each time you have a loop, actually it is very fundamental to have this kind of going back and forth between combinatorial properties and the group property. Any questions about that?
Sir, I had a question.
Yes, please.
So when we are looking at the generating set, we are considering modulo the inverses, is it? Like
exactly. Yes, I want to. So here I didn't write down the inverse, but it's you have to add them down on them.
Okay, yeah, fine.
There's no real convention, unfortunately, about that. So usually, either people look at what they call symmetric sets, symmetric generating sets, meaning that each time you have an element, you also have its inverse. Or you don't, and then you add the inverse when you want to make the Kelly graph.
Yeah, true.
Okay?
Yeah. Also, when we computed for the word metric, so basically we showed that D is like, G is like the isometries, right?
Yes, well, it might not be the whole isometry group. You see, for instance, when you have the four regular tree like this. So what we do, you could also rotate the tree about one vertex. And this does not exist. You see, you have no fixed point by the action of the group, for instance. So this is not, so this is an isometry of the Kelly graph of the free group, but it is not an isometry. It does not come from your group. So the automorphism group can be larger than the group you're starting from.
Okay, yeah, okay.
But you see, the isotropy group is always finite because you have only finitely many edges to start. No, it's not true. It could be infinite depending on some case. I'm sorry, I should not say that. It's not finite, I'm sorry. Because you can switch at every level. So you see, it's even infinite indexed, the group G inside the group of automorphism. You have a lot of possibilities because you can, I could, sometimes it doesn't want to. No, it's not the right color. You see, you could switch these two also, or switch these two, because it's completely symmetric, and so this gives you a lot of elements, uncountably many, I suppose, maybe. I don't know. Or at least countably many. Okay. Are there any other questions?
Not from my side. Thank you.
You're welcome. So now let me go to something fundamental here. So it's geometric action. Actions. So here I assume that X is a metric space. Okay, and I assume that it is proper. And this means that each time you pick a ball of finite radius, a closed ball of finite radius, centered at the point X, then this is compact. So the compact subsets are the bounded and closed sets. And I will assume also that it is a geodesic, in the sense that probably the same as what Arnaud defined in the setting of Riemannian manifolds. So it means that each time you pick 2 points, X and Y, you can find a curve of length exactly the distance between the two. Okay, so another way of saying that is that you have an isometric, there is an isometry from the segment 0 to the distance between X and Y in your space X, such that for any elements T and S, the distance in X of the image of S and of T is exactly the absolute value of the difference. And also what you want is that the starting point is X and the ending point has to be Y. So each time you pick 2 points, then you have a curve that joins the two. And so you see here what I have represented in the black line. It is the image of this segment by my embedding I. Okay? So now I look at an action G at a group that acts on X, and I say that this action is geometric. If 3 properties are satisfied. So the first is that it acts by isometries. So meaning that it is distance preserving. Then I want the action to be properly discontinuous. And this means that each time I pick 2 compact sets inside my space, like balls, for instance, closed balls, because my space is proper, then the set of elements G, such that when I take the image of K by G, it intersects L, I want this to be finite. Okay, and the last property is to be co-compact. By this, I mean that you have a compact set, K in X, such that all the translates of K under my group G covers the whole space X. Or in other words, the quotient with the quotient topology is compact. Okay? And so the basic example that you have to keep in mind is a group G that acts on its scaling graph. Okay, you can check that these 3 properties. So I already explained why it acted by isometries and why it was co-compact. So the only last property I want to define is to be properly discontinuous. And so the fundamental lemma of geometric group theory tells us that essentially there is only one, and it also says something about the group. So let me let me state this lemma. So this is called the Schwarz-Milner lemma. So Schwarz is this a weird way of writing it, or it is oops. So you assume that G acts geometrically on a proper geodesic matrix space. Okay, so then two things. First, G has to be finitely generated. And second, given a finite generating set S a finite generating set, we have the following property. So I pick, there is some constant lambda that is at least 1 and C that is positive, such that if I look at the distance and I pick a point, so that for any point X in my space, if I look at the distance from G of X to H of X in my space X, this is at most lambda times the distance from, with respect to the word distance between G and H up to some constant C, and this is at least 1 over lambda the distance from G to H up to C. And the second property is that if I look at the union of all the balls of radius C centered on the orbit of X, it covers the whole space. Okay? So let's just remind you of the simple examples with the cyclic group Z with a set of integers. Okay, so what it tells you is that, so here what you obtain is an isometry because it is uniquely done, but you see, yes, a very good example. But the thing is that these maps, this property means that it is almost by Lipschitz if we look at very big distances, because then the constant C becomes negligible in some sense. And so what it says is that if you look at two different Cayley graphs, you will have something that depends up to these additive constants, and the Cayley graphs will look the same. And so when I had this other generating set with the blue thing, it looked like this, remember? And similarly, the other way downstairs. And so you see that these two graphs, they have this kind of property here, and this is what will define for us the notion of quasi-isometry. And so, so then this motivates the following definition. A quasi-isometry is a map between two metric spaces such that there are constants lambda at least 1 and c non-negative, such that when I look at the distance between the images of 2 points, x and x prime, it is at most lambda times the distance from x to x prime up to an additive constant is at least 1 over lambda the distance from x to x prime minus c. And if you look at the union of all the balls centered at the images of the point of radius c, then it covers the whole space x. Okay, so this property 2 leads us to the definition of a quasi-isometry. And so the one thing that we want to do is to understand groups up to quasi-isometry, because then it means that we can look at any Kelly graph. They are all quasi-isometric to each other, one another. So it means that a property that does not depend on the Kelly graph, a property that is invariant by quasi-isometry, it is a property that won't depend on the Kelly graph. And so it will be a property of the group. And this is how we're going to try to look at that. So in the time being, in the time that I have left, what I would like to do is give a sketch of the proof of this lemma, because it's very important. So it's in the second video that I've done. And there are several exercises that you will do, that depends maybe on this proof. So I think it's important to see it. Is the statement clear? So we have exercises that explain also that make you manipulate quasi-isometries, and also this lemma and some other examples on Kelly graphs, etc. So I will. Okay. So the proof of it. So first, I want to find a finite generating set. So I assume. So I know that the action is co-compact. So it means that there exists some compact set K, such that the union of all the K's is capital X. This is my basic property of geometric action. So then I fix D, the constant D, so that for any X in K is included in the ball of radius D over 3, the open ball. Yeah. Okay, so I pick D over 3 because I already know how the proof goes through. Otherwise, I will cross it to something different. And now I will define S. It will be the set of elements of my group G, such that wait, I have to fix also a base point that I call W. G of W belongs to the ball of radius W, centered at W and of radius. And so first I claim that S is finite and generating. Okay, so what I say is that it is finite, but this comes from the fact that it is properly discontinuous. Okay, it's enough to, for instance, you can look at the compact set L1. So I have to change letters, otherwise it will be. You can look at L1, it will be the singleton W, and I can take for L2 the set, the closed ball. I mean, yes, so this is not good. So the elements that are in my set S In particular, they map W. These are those that when you take the image of L1, they intersect L2, because I took something a little bigger. And since the action is properly discontinuous, I know that this is finite. So this proves that it is finite. Actually, this one is also symmetric, but this is not important for what we want to say. So now I would like to do is to explain is that why it is a generator. So for this, I pick any element G in my group. So I have my element W here, and I have G of W somewhere. And I want to say that, to prove that I can write G as a product of elements of S. So for this, I look at the geodesic which joins the 2 points. And what I do is that I cut it into pieces so that I call xj. Different points is exactly d over 3. And so W will be equal to x0, then I will have x1, etc. And the last, of course, it's not a multiple, the distance between W and G of W is not, and here it will be, I will call it xn, and the last here, the segment is at most d over 3, but it can be much smaller, of course. But this is not very important. So now, what I know is I have this co-compact action, and the way I have fixed domain, my number d, means that for any xj, I can find an element on the form gj of w that is at this, sorry, I will change colors here. The distance here, I wanted to change colors. The distance here is at most d over 3. D over 3. And so similarly here, I have something smaller than d over 3, and it will be connected to some gj plus 1. Here I pick for x naught, I pick the neutral element, E of, so we're going in that. I want G0 to be the neutral element of the group, and Gn, it will be exactly G. And so, I want to, what I get by the triangle inequality is that the distance between Gj of W, Gj plus 1 of W, it is at most the distance from, so maybe I'll be a little faster. So it will be the distance from Gj of W to Xj. So this is at most D over 3. I have to kind of put my hands. Then, actually it's strict because it was in the open ball. If you, no. Then, from Xj plus 1, and then from xj plus 1 to gj plus 1 of w, this is again d over 3. So you see, this is exactly d. And because the group acts by isometries, this is the same as the distance from w to gj inverse, dj plus 1 of w. This is before. And because I can multiply by gj, you see this means that it moves w, this element gj inverse times gj plus 1, it moves w at a distance at most d. So this means that this element belongs to S. what I obtain in this way is that my element G, that is Gn, I can say that it is G0 inverse times G1, G1 inverse times G2, and I continue like that up to Gn minus 1 inverse times Gn. Okay, and if I put the brackets like this, what I get is that every element here is in S, because just above. And so it means that and this is Gn is exactly G. So here G can be, the norm of G is at most N. It can be written from S. And so here I've already proved that what happens when the group is geometrically finite. So having some geometry property on some action gives you some algebraic property of the group to be geometrically finite, to be finitely generated and so on. Okay, so now I don't know if I can use 5 minutes to conclude the proof. I know I'm getting out of time, but do I have a little more time then to conclude? Okay, so if nobody complains, I will use. So now what I want to prove is this quasi-isometry bounds that I have. So let me remind you that I already know that G is smaller than N. Okay. And so the drawing was W, G of W, Xj plus 1. So the first thing that I can say is that if I look at the distance from W to G of W, this is, because I'm on geodesic, the sum over k equals to 0 to n minus 1 of the distances from xj to xj plus 1. Okay? This is just because it is a geodesic. And now remember that I have no concept that this is at least the sum where I stop to n minus 2 of the same thing. Okay. But now these distances, I know them. They are exactly d over 3. So this is, and how many elements do I have in this sum? How many terms? I have exactly n minus 1 terms times d over 3. And that, it is at least the norm of G times n minus, times the d over 3, I'm sorry. Times d over 3 minus d over 3. So you see here I have proven one inequality that I had before. And for the other inequality, this is more standard. So you take G and you write it as a product of elements of S, where K is the norm. Okay. And I let M to be the maximal distance between W and S of W when S ranges my finite generating set. Okay. So what can I say? Well, I will say that the distance from W to G of W, this is, by the triangle inequality, the distance, at most the distance from W to S1 of W, plus the distance from S1 of W to S1, S2 of W. Then I get to something like the distance from S1 up to Sj of W to S1 up to Sj plus 1, Sj plus 1 of W. And then the last term that I will obtain is the distance between S1 up to Sk minus 1 of W to S1 up to Sk of W. Okay, this is just a triangle inequality where I put elements on the right. So let us know that when I do this, I'm looking at a path inside the Cayley graph, because each time I multiply on the right by an element of S. Okay? And so now I use the fact that it is an action by isometry. So the distance from S1 of W to S1, S2 of W, this is the same as the distance from W to S2 of W. And the same here, I have in common S1 up to Sj on the left and on the right. And so since it's an action by isometries, this is the same as the distance from W to Sj plus 1 of W. And in the end, the last term that I get is the distance from W to Sk of W. Now I know that each one of these terms are smaller than n because it is an upper bound. So this is bounded by how many terms do I have where I go from S1 of W up to S1 Sk of W. So I have k terms times n. And k, this is exactly the word norm, so the word distance between the neutral element and G. So this is equal to n times the distance in S of E to G. Okay, so this is the second inequality. And then to conclude the last inequality, the last condition, we were saying that I was covering everything, but this is just the co-compact action. Because what we already know is that X is the union over all translates of the Bohr of radius D. Even D over 3 is of G. And so this concludes the proof of the Schwarzschild-Miller lemma. That tells us that essentially up to quasi-isometry, there is a single action, geometric action of a group. Okay, so I think I've talked enough for now. So I will stop, and if you have questions, then I'll be glad to answer. So thank you for your attention.